Hey there, welcome back to Short Text 331. Today we're going to talk about part 2 of the calculation of the Green's function for diffusion in 1D. And if you recall, then last time in part 1, we aimed to solve the inhomogeneous diffusion equation, which is an equation that looks like this. And in previous videos, a few videos ago, we were talking about solving for basically the left-hand side equal to 0. So df dt minus second derivative of f with respect to x twice equal to 0. That's the homogeneous version. But now we want to solve this one where you have an inhomogeneity, something that drives the system and is usually given as part of the problem. And we're also usually given a function that determines the initial condition. So we're just going to call that f of x comma 0 because that's where the time variable goes. So we set that to 0 and that's our initial condition. And basically what that amounts to is putting this differential operator that we call d here on the right hand side of the equation. So we have df equals j, and so we want to put the d inverse on the other side of the equation, and so we get f equals d inverse applied to j as an operator. And what it amounts to applying this inverse operator is to do this convolution, sometimes called convolution product, between the Green's function and the inhomogeneity or source j. And so this is what we saw last time, and the Green's function is then determined by this equation. So d times g, or d applied to g, is equal to a product of two deltas in space and in time. And of course, the Green's function has all these variables x, t, x prime, t prime. We integrate over x prime and t prime, but we leave x and t as the variables that define the function f, that become the arguments of the function f. And so we need to solve this equation, and we saw, or it's easy to see that once you solve that equation, then if you apply the operator d on the left-hand side of this equation, then it travels right through the integrals. It applies to g on variables x and t. It produces these deltas, and so then the integrals become trivial, and right away you recover j as expected. In other words, you obey this equation right away. And after a fair amount of calculation, we determined that the Green's function then has this form where we have this heaviside theta function, and we have this square root and a factor, and we have also a Gaussian factor as well, which was familiar from diffusion processes, even in the absence of any source. So we saw that in previous videos. And so now what I want to do is to say, well, suppose that we're given a j, we're given a function j, and suppose it's this one. It's a simple, pretty benign function, e to the minus x squared, e to the minus t squared. So if you want, this is like a Gaussian that starts to turn on from minus infinity, where it's completely 0 because this factor goes to 0, and then it reaches a maximum at t equals 0, and then it dies off again as t goes to infinity. So we're driving, if you want, this shape, this Gaussian shape, from being completely flat at t equals minus infinity to being a full profile of e to the minus x squared at t equals 0, and then beyond that it goes on to decay again. So this is what drives the diffusion process, if you want. And so our job then, taking into account that the Green's function has this form, is to carry out these two integrals. So what we have here then is an integral over time. It goes from minus infinity to t because this is cut off by this theta function. So t prime is cut off at values less than t, and so it goes from minus infinity to t, and then we have an integral from minus infinity to infinity of this whole complicated mess of stuff that depends on x, x prime, t, t prime, and so on and so forth. And so we need to do these integrals. So a couple of questions here. The first one is, what about the initial condition? So how do we know that this solution actually gives us the right initial condition? And in fact, it doesn't, and we don't know right away. We built some Green's function that obeys the properties that we want. It does obey this property. It satisfies some initial conditions that we were not very, very careful about. So at t equals 0, it's equal to some value that is not predetermined, and it doesn't necessarily obey any given specific form, f of x comma 0. So we didn't involve that at all in solving for our Green's function. So we need to address that problem. So how do we build a solution that really obeys the initial condition that we want? And so if you look at this solution that's here, just a convolution of the Green's function with the source, what you get is this integral here. So of course it's just the integral between minus infinity and 0, at t equals 0, I should say. If you evaluate that function at t equals 0, then you obtain this form, integral from minus infinity to 0, and then everything else stays the same. And this is equal to some function that depends on x. So notice there's no t here, so t was set to 0 everywhere. We only have x, and then the integration variables x prime and t prime. So this is a function of x once the integral is done, and it's not in general going to be equal to any initial condition that's given to us. And so we need to correct for that. So how do we enforce then that our solution f of x comma t goes to a given form f of x comma 0 once we've accounted for j already, because that's what the Green's function does. The Green's function helps us to account for j, but it sort of messes up the initial conditions f of x comma 0. So how do we fix that problem? And the way to do this is actually pretty common, not just in diffusion, but in other applications as well, in waves and also in the Laplace equation. The way to attack this problem is to do this, to say our solution f to our problem df equals j has two terms. It's going to have a term that is, as we already wrote, the inverse j, and there's going to be another term that will fix our problem. And it has to be a solution of the homogeneous problem dh equal to 0, and that will fix the initial condition, as you will see. And the rationale behind that is that if you propose this solution now, then df, when you apply the operator d to f, is going to be equal to d, the inverse, to apply to j, so it's of course equal to just j, because the inverse is just the identity, plus another term that's d applied to h. But if d applied to h is just 0, if we force that to be the case, so it's a solution of the homogeneous problem, then we're in business. Then df is still equal to j, and we didn't mess up what we accomplished with our Green's function. Now, when you evaluate our new solution at j equal to 0, sorry, at t equal to 0, then you get f of x comma t going to our g of x, which we define above, which is basically whatever the Green's function part of the solution converges to. And so that's going to give us our function g of x, plus some h of x comma 0, which is to be determined, which we haven't said what it is yet. And we want that to be equal to the given f of x comma 0. So this is a piece of information that's given to us. This g of x is imposed on us by a Green's function part of the solution. And so this is what we need to fix in order to finally solve the problem. In other words, we're going to require our function h of x comma t to be a solution of the homogeneous problem dh equal to 0, and now with initial conditions given by h of x comma 0, which is by force, we're forcing this to be equal to f of x comma 0 minus g of x. And so what that will accomplish, of course, is that when you evaluate at t equals 0, then the g of x gets cancelled and we recover the initial condition that we want. And we accomplish all that without spoiling the result that we already have, the df is equal to j, by adding this dh. And so that's no problem at all. And so that now is really the solution that we want. So we want then a solution that takes, once again, this form, f equals d inverse j, a part that we discussed already is the convolution of the Green's function with the source j, and then we add another part that is a solution of the homogeneous problem. And this is a very common approach to solve this, like I said before, and not only in diffusion but also in waves and in the Laplace equation. You are allowed to add a solution of the homogeneous problem without spoiling this property df equals j to solve, or rather to fix your initial condition, or sometimes boundary conditions as well. So you may think, well, this means we didn't really have the right d inverse, because we put d on the other side of the equation as d inverse, and we didn't solve the problem. In a way, we had a d inverse that it works if f of x comma 0 is just 0, and so okay, so that solved the problem for that case, because as I said before, we completely ignored the initial condition when building g, but that's okay. That's okay. What we have here is simply a reflection of the fact that the kernel of d is non-trivial. So our operator d for diffusion has some non-trivial solutions even when the right-hand side is 0. It's a linear operator, but its inverse is not really well defined, as we are seeing here. There are non-trivial solutions f when that depend on initial and boundary conditions, and even though d is a linear operator and the right-hand side is just 0. So if d were a completely regular operator with no issues, then of course the only solution to df equal to 0 would be 0, but that is not the case. We saw before that this diffusion equation df equal to 0 does have all sorts of non-trivial solutions, and so this effect that we're finding here, that we don't obey the right initial conditions, but we're allowed to add this. This new term is perfectly normal, and it's just a reflection of that property that the kernel is non-trivial. Now let's move on then to a more specific example. I want to show you some plots of what the solution does. And so for simplicity, suppose our initial conditions are not at t equals 0, but let's take them to be at minus infinity. And suppose that our initial conditions are just that f of x comma t goes to 0 when t goes to minus infinity. And so basically what we have here requires no h. So if you want h is just 0. So this extra term that we need to add in the most general case, doesn't need to be added here. So when you take our solution given in terms of the Green's function, which I showed up here, let's see up here, if you take t to minus infinity, of course, this goes all to 0, and you can convince yourself of that. And so there's no extra thing that we need to do, and so we can focus on the part of the problem that uses the Green's function. And so suppose then that's the case, and so we're going to focus on just the Green's function term, and that's convolved with the source. And as we said before, the source is given by this. It's just the product of two Gaussians in space and in time. And so what does that do? Well, when you do that integral, the double integral in space and in time, this is what it looks like, evaluated at various times. At very early times, so this is in fact the negative time, it starts to pick up this shape. The solution starts to behave like this, and as time progresses, it starts to grow by virtue of the fact that our source is inserting energy, or if you want, is inserting a non-zero contribution into the system. And so as we get to higher and higher times, so later and later times, it reaches some maximum, and then after that, as we go from T5 to T6 to T7 to T8, it decays again, and eventually goes down to 0 at very, very large times, as it is not driven by anything. This is a typical type of behavior that you would expect from this type of source. But if you look at this type of source, you also see that the maximum is obtained at t equals 0. So in other words, this is if you want, an envelope, e to the minus x squared is a Gaussian with an amplitude that varies from 0 to a maximum of 1 and then back to 0 again. So when t is 0, then this reaches the maximum. But the maximum here is not reached at t equals 0. So I didn't tell you exactly what times these are, but the maximum is not reached at t equals 0. And to show you that, I plotted down here the behavior of our solution at the origin, so here at x equal to 0, as a function of time. And so you see that here, and you see that the maximum is not reached at t equals 0, it's reached a little later, and that's because this diffusion process is a little bit delayed in accumulating the effect of the source. I encourage you to play with this. This is something, as you can see, I've plotted this with Mathematica, and as I always say, Mathematica does not endorse any of this. I just use it as a tool. It's very simple to use, and if you don't have Mathematica, you can use Wolfram Alpha. It will be just fine. I'll give you a piece of advice when doing that, by the way, just for the sake of speed. If you want to plot this type of complicated function of space and time, let's say at a given time, it is helpful to ask your engine, Mathematica, or whatever you use, to do the integral over x prime first. If you look carefully, the dependence on x prime is entirely Gaussian. It would have to complete the square and so on, and you probably could do it yourself again by completing the square on x prime and carefully doing that calculation, and then one of the integrals will be done for you, and so you don't have to ask your engine, whatever it is, to do a double integral numerically. You can just have it do one, because again, the inner integral over x prime can be done analytically. So once you have that, then it will be very easy for you to plot these types of curves at different times, and again also this curve at fixed position as a function of time. Finally, well, I already mentioned, note the delay between f of x t and versus j of x t, and if you want, you can plot here what j of 0 t would look like, and it goes up to 0 and then it goes down again. So if you put x equal to 0 in our j, here of course you just have that nice Gaussian in time, but the effect on the system, which responds via the inverse of the diffusion operator, is a little delayed like this. And that's just the effect of diffusion. I want to mention that we use contour integration in obtaining g of x t x prime t prime, so the Green's function, and we'll talk more about that in future videos. In the previous video, I sort of pulled out of my hat the effect of doing that contour integration, and this is not something we've discussed in detail in this channel, so we'll come back to that when we dive a little deeper into complex analysis, and then you'll see exactly how to do those integrals and what theorems are behind doing those integrals, such as the residue theorem that I mentioned in the previous video. And finally, I want to emphasize that, once again, this is a very, very common way to approach the problem of solving linear inhomogeneous partial differential equations. So you will have a solution given by an inverse of an operator, which typically will involve a Green's function applied to the source, the inhomogeneity, and then you may or may not need to add an extra term that fixes the initial boundary conditions, and that term will necessarily obey the homogeneous equation, which could be the homogeneous diffusion equation, it could be the Laplace equation, and so on, or the homogeneous wave equation, or whatever it is that you're dealing with. And it would have to be this way because this first term deals entirely with addressing the presence of the source. And what we're doing here, of course nothing other than superimposing two solutions that will give you what you want. And this principle, the idea that you can superpose two solutions to give you the solution that you want, is of course also very common in linear equations. And that's it. That's all I have for you today. I hope you enjoyed this video. If you did, please consider liking and subscribing to the channel. And as always, if you're looking for a tutor in physics or math, in English or in Spanish, I'm happy to help you. You can reach me at shorttakes331@gmail.com, or you can leave a comment in the comment section below, and I will get back to you as soon as I can. And that's it. I'll see you next time.